We are working on the partition problem, and the partition problem wants you to determine if a given set can be partitioned into two subsets such as the elements in both subsets is the same. So as we can see in line 9, we're given a set and we want to see if we can partition it into two subsets such that the sum is the same. And as you can see in line 11, it can be partitioned into two sets, 1, 5, 5, and 11, and both of them have the same sum. So the question is, when you have a problem like this, is like, how do you start? How do you start thinking about it, and how do you start thinking about solving it? So one of the ways I think about these types of problems is like to think about how I would try to solve this problem without a computer, but try to do it in a very systematic and organized way. So what do I mean by systematic and organized? So what I mean is that try to solve this problem by creating smaller problems that have the same structure as the current problem. So I think that takes a little bit more explanation. So let's look at an example. So we are given this array, the set, and we're trying to figure out if we can partition it into two subsets such that they have the same sum. So the total sum in this array is 40. And so that means we want to create two subsets such as the sum is equal to 20. So let's just write that in one line. Target. So we have this, and our target is equal to 20. So the way I do this is I usually start on the right-hand side, and I want to figure out if I should take the 2 or not in my subset. So I know there's two subsets that you need to know about, but you only need to track one subset. Why? Because the elements in your big set, not in your subset that you're tracking, will be in the other subset. So if you know one subset, you kind of know what the other one is. So the thing is that our target is 20, and my local decision is, should I take this 2 in my subset? And so if I take the 2, so take 2 in a subset, then what I'm left with is a problem where I have these elements only. I have to figure out if I should take these elements. But when I take 2 into the subset, what else is changing about my problem? And what you'll notice is that when I take 2 in my subset, that means that the rest of the elements that I'm going to take in the future only have to equal 18. They don't have to equal 20. So what's actually changing is the target itself. So target is now 18. So I don't know if taking 2 is the right answer. So I have to try out if, like, what happens if I don't take the 2 in my subset. So if not take 2 into subset, what happens? So I'm still left with this same problem here. So in terms of the array, so I didn't take 2, so I still am only left with these numbers. But what happens to the target? The target doesn't change. The target that I'm trying to reach still stays 20. So I still have to try to see if I can get 20 from the elements that remain. And what you kind of notice is, like, if we look at the problem in line 7, and we look at the problem in line, so let's put a star. We look at a problem in line 7, we look at the problem at line 11, and we look at the problem in line 15. What you'll notice is that the problem on line 11 and line 15 are very similar to the problem in line 7. The only difference is that the target is different, and the elements in the array is just one element smaller. And so if you notice that we can also, like, hypothetically say our our uh, our initial problem, we call it V, and we give it an array, and we give it a target, and that target is equal to 20. We can write, we're now stuck with two smaller problems here. If I take 2 into the subset, I have this problem. If I don't take 2, I have this problem. And so the question is, like, if I know the solution to these two problems, can I solve this bigger problem in line 7? And so what I want to do is I want to see if I can take the best of these two. So if, for instance, in line 11, if this target, if in line 11, if it's true that we can hit a target of 18 with these elements, then I know it's going to be true that I can hit a target of 20 if I've taken the 2, because 18 plus 2 is 20. Similarly, it could be the case that if I don't take the 2, I hit a target of 20, and that's good too. But the thing is, it could also be the case that the target of 20 is not hit by something in line 15. So if we think about mathematical induction, so mathematical induction, one of the things is that it says is that you have to have two things to be able to do it. You have to have a small trivial problem that you can solve, and then you have to show that a smaller problem will be able to solve a larger problem, will help you solve a larger problem. And so if we look, so usually mathematical induction is done using dominoes as an example. So you're given a set of dominoes, as you see in this picture. Sorry for my bad drawing skills. So what you see is that if you can knock down the first domino, you want to show that if I knock any other arbitrary domino down, so say this one, that'll knock the next one down. So usually it's graphically shown like this. And you eventually hit the top. But our problem is a little bit different. Our problem, what you see is that if we think of the problem in, like, say, line 11 as the smaller domino, or the line in 15 smaller domino, we actually have, and say line 7 is the last domino right here, we actually have two dominoes that could possibly knock down the one in line 7. So our picture is really not like this. Our picture is really like this. So we have a set of dominoes on the left, which could represent line 11. And then we have a set of dominoes on the right, which can represent line 15. And so we want to figure out which one of these two sets can actually knock down this domino. And so it's true that either one of these can knock it down. So, but what we want is we want to take the best one. So if we look at this picture here, so we can see that the blue is knocking down. If the blue hits it, it'll go this way. This last domino will go right, and if the red ones hit it, then it'll go left. And what we want is, because it could go either way. We get to choose which one we want to hit the last domino, and what we usually want is the best of the two. So say best is a function, and it takes two arguments, and so we want the best. We want to take the result of the best of these two functions. So once we know what the best is, we could use that to knock down the last domino. And so that's how mathematical induction works here. So let me give you an example. So if say the one with, if we look at line 19, if best is defined by if it's true, if the partition problem can be partitioned, we want, and we get true that with target value 18 and the smaller problem, it can happen. And if with target value 20 for this second one right here, if we get false, we want the true because we know that's good. We've decided that best is going to be whatever offers us true. So we could write our best function as because this is going to give true or false. So we want the value of this first subproblem right here if it's true, or we want this one if it's true. And so if one of them is false, it doesn't matter because that means if one of them's true and one of them's false, that means that, hey, the partition problem can be solved. If both of them are false, then it means that we can't solve the partition problem for this bigger problem in line 7. And if one of them's true, that means that one set, like taking the 2, so if this part taking target value 18, this means that taking the 2 actually made a difference, and it helped us solve our problem. So if this is true, like if we can get a good subset out of here and then add 2 to it, and it solves the problem, then that's great. So that's how mathematical induction is helping us kind of get intuition on how to think about the problem. Because now we know that we have to figure out which one of these two things is knocking down our final domino, which is our bigger problem. And the other thing that I mentioned is that in mathematical induction, you have to also be able to solve a trivial version of the problem, which is also known as base case. And the thing is that base cases can sometimes be very tricky to come up with. And what I'm going to show is like later on is like how we can walk up that abstraction ladder to help us like find the base cases and help us like systematically take care of the base cases, so it's less likely that we forget them. Because we have two set. If we look at our problem again, as you can see, we have actually two variables. We have to keep track of the array, what's remaining in the array, and we also have to keep track of the target value. So base cases can be a little tricky in examples like that.